Okay, here we have the next problem. I noticed on the last problem, the time it took me to work this problem on the board is about the time I would expect a student to be able to work it on the exam. It's kind of funny how it worked out that way. Next problem, electrostatics. We want to know the magnitude and direction of, here's a point, halfway between the two charges. In other words, it's 0.141 nanometers between these halfway point. So from the positive charge to the halfway point is half of this. And from the halfway point to the negative charge is also half of this, also 0.141 nanometers. So we want to know the electric field magnitude and direction halfway, the voltage halfway, that's part B, and the force on each charge. This is simple electrostatics. The charges, this is rock salt. The charge on the positive ion is one electronic charge, and the charge on the negative ion is negative the electronic charge. And the constant K for Coulomb's law is that. Okay, part A, electric field. Now, first of all, we recognize electric field goes from positive to negative. So we're going to have an electric field vector due to the positive charge in the positive x direction. And this is supposed to be a positive down here. There we go, positive charge. We have the negative charge over here. It's also radial to the negative charge. It's on the line between the positive and negative charge, and it points toward the negative charge. So the influence on the electric field due to the negative charge is in the same direction, in the positive x direction, which of course is symbolized by the unit vector. Now that we've got the direction, we just need to figure out the magnitude. Well, the total electric field is just the sum of the two. The positive electric field is K, charge on the positive, radius, the distance from the positive charge to the halfway point, plus, now we know it's in the positive direction, so we've got this going on, divided by r squared. And both of these are in the, they're pointing in the same direction. The magnitude of the negative charge is the same as the magnitude of the positive charge, and the distance to the halfway point is the same for both of them. So we can just go 2k q plus over r squared, and it's in the x direction. Now it's just plug and chug. Take all the numbers, put them together. Go back to my calculator. There's the calculator. Clear it out. 2 times 9 times 10 to the 9th. Times 1.602 times 10 to the negative 19th, and then divided by 0.141, and that would be nanometers, which is times 10 to the negative 9th meters, and that would be squared, equals, and I'll turn it into scientific notation, 1.45 times 10 to the 11th. Rounded to 3 sig figs, of course. And that would be newtons per coulomb. And in the x hat, in the x direction. Okay, B, what is the voltage? Well, the voltage is equal to the sum of k q plus over r plus k q negative over r. Of course, this is just the equation. This is just the voltage equation for summing voltages due to individual charges. This q minus is equal and opposite to q plus. K is a constant equal to this. R is still 0.141. In other words, this factor is positive, the same value as this is negative. They're equal and opposites. When they sum, they equal 0. 0 volts at the midpoint between the two. C, so that's a quick answer. C, what is the force? And the first thing I want you to recognize is the force on the positive charge due to the negative charge is equal and opposite to the force on the negative charge due to the positive charge, and they're both and they're attractive. They attract each other. This is just Newton's third law. Equal and opposite forces. So once we get the force direction of one, we get the force direction of the other, and we just simply use Coulomb's law. Force equals K Q plus Q negative over the distance between the ions squared. I'll go D squared. D is twice R. That's 0.282 nanometers. I intentionally asked the question this way to get you to recognize I can't just take electric field and multiply it by charge, because you want the electric field at this point multiplied by the charge at this point. You have to go through the calculation, and you would find, of course, the force would be that. And it's in the positive or negative x direction depending on what is acting on what. So F plus would be greater than 0. It's in the positive x direction. F minus is in the negative x direction. Okay, so now it's plug and chug. We have K's, we have Q's. The magnitude of the force equals 9 times 10 to the 9th times 1.602 times 10 to the negative 19th, and I multiply them together. There will be a negative sign involved. I'll remember it. I won't actually put it in the calculator. D is 0.282 times 10 to the negative 9th meters, and that's squared, equals 2.90 times 10 to the negative 9th. As long as we're consistent with our units, the force would be in newtons. F positive in plus in x hat direction, the force on the negative charge in the negative x direction. End of problem. Ready to go on to the next one. And before I do that, I just want to check the time. Okay, we've been going so far for about 9 minutes. This is a 15-point problem, so it took 9 minutes to explain the problem. I expect you to be able to perform it in 15 minutes. Now I will end the recording.